3, 7 through 4, 3. By the way, if anyone has homework that they wanted to turn in a hard copy of yesterday, obviously, I'll take that. And then any problem sets that are hard copies I will take as well. Thanks, man. Nice. 9, 1, 4, 3. Well, did you give me 4, 1, and 4, 2 already? Because this is 3, 9, right? And then this is 4, 3. 4, 1, and 4, 2 we're due another day, a different day. So see if you have it still. Because I don't have any papers to give back to you, so I'm thinking that you probably have it still somewhere. All right, so if you recall, 3, 7 was our systems of linear inequalities. What did that mean? Systems of linear inequalities? We have a short period, so if you guys want to let that down, let's answer quickly. Systems of linear inequalities. What's an inequality? James?
Comparing to things, you graph them and you shade it.
Yeah, this is the examples where we graphed and shaded. Not very difficult to respond, right? So we have two functions. Let's say we have, for example, y less than 2/3 x plus 4. And let's say 2x plus 4y greater than or equal to 17. 17 is fine. Okay, if I want to graph these two, the first one is a less than symbol. What does that indicate to you? What does that make you think of when you see the less than symbol in the first one? James? Yeah, we're going to shade below that for sure, because it's y is less than. But the second one, I can't assume that I'm going to shade above, correct? Because in the second one, I don't have y greater than or equal to. It's just a statement with a greater than. If you're going to use the less than or the greater than sign to indicate where you should shade, it needs to be in slope-intercept form to do that. The first one is already in slope-intercept form, so James is absolutely right. We shade below. Now, if it's a less than sign as opposed to a less than or equal to sign, how does that change the graph? The first one is a less than sign. The second one has a greater than or equal to. Not having the equal to below it, what does it do to the graph? James?
Makes it a solid or a dashed.
Yeah, which one would the first one be, solid or dashed? Yeah, this is dashed. Why is it dashed? It's dashed to indicate that you don't actually get to that boundary. You shade in the region below it, but you don't actually get to that. It's not included in the solution set. So I can tell you already that this is going to look like this. Oops, I should make it dashed, as I just said. I'm sketching, obviously. I have no axis labels or anything. I'm doing it quickly. The y-intercept was 4, the slope was 2/3, so it's positive. The y-intercept's positive. So I'm literally drawing you guys a real quick sketch. The second one, though, how would I draw a sketch for that real quick? What's the easy way to do it? You mean you could put it into slope-intercept form. What else could you do? How do you find the slope in the second one? But it's in standard form. Yeah, negative a over b. So for the second one, the slope is going to be negative 2 over 4, or simply negative 1/2. There's the slope. The y-intercept is c over b. That's 17 over 4, which will give us 4.25. So there's the second one right there. A slope of negative 1/2 and a y-intercept of 4.25. So that means that y-intercept is going to be just above the other one. The first function we graphed had a y-intercept of 4. This has a y-intercept of 4.25. And it's a negative slope now, so let's do that. So that's what that one would look like. So notice, I'm pointing to it so you can see. This y-intercept is just above this y-intercept. This is a y-intercept of 4. This is a y-intercept of 4.25 from here. This is a negative slope, so I generally just drew a negative line. Or sloping line that's negative. At this point in time, James is right in the beginning. We can definitely shade underneath the dash line because of this less than symbol, because it's in standard or it's in slope-intercept form. So we can definitely start by shading under here. Now the question is, do we shade above or below the solid other line that's kind of yellow there? Not orange. This one we're doing is orange. Do I shade above or below? How do I know? What's the easy way to figure it out? Don't put it in standard form. It's more work.
You can plug in the origin.
Yeah, plug in the origin, okay? So you do not need to convert. I keep saying standard. I'm thinking standard because polynomials we call it standard. Don't put it into slope-intercept. So yes, plug in the origin. 0, 0 tells you 0 is greater than or equal to 17. Is 0 greater than or equal to 17? Is it? No. So you don't shade the side with the origin. So we do not shade this side of the line as a result. You do not shade this side. We shade this side of the line. So we do that on this side. Well, where is there a crosshair, or where is there a crosshatch pattern? It's obvious, right? All we do is put a big S in that region. Okay, that indicates that the solution set is there. And again, that solution set is 1/4, if you will, of the possible answers you have. There are really 4 regions if you think about it. When 2 lines intersect and have an intersection and they're not parallel to one another, right? Not infinitely intersecting, you always are going to get 1, 2, 3, 4 regions always. Again, because they're intersecting right here in the middle. There's their intersection, okay? 1, 2, 3, 4 regions. Only going to shade one of them. Yes? Make sense? Okay. We had a question like this, I think. I remember, on one of your old quizzes, I think I had you do one of these real quick. Okay, you should definitely look at that as an example. What if I told you another thing like this? What if I said this? What if I said x is less than or equal to, let's say 12? What would that do? How would that alter this graph? And I know there's no number, so just do your best to estimate. How would I do this? Yeah, put a vertical line that goes through x equals 12, right? Let's say 12 is right here. Okay, hypothetically, I don't have numbers. Let's say that's 12. Well, then I would realize that if I'm connecting these, this dashed line continues, right? My solution set would really be this triangular region. What does less than 12 mean? It means that everything to the left of this line is possible for the answer, but everything over here is not in the answer. So since this was our region of solution right here, right? This was our solution region. This is no longer in the solution because it's got to be less than 12. So this triangle that I'm outlining is your solution region right here now. Does that make sense what I'm saying? Okay, I could do x or I could use y. I could use greater than or I could use less than. I could use less than or equal to or greater than or equal to. There are an infinite amount of possibilities here. Okay, if I just change the line and change the number up. So for you, practice it. Literally make your own 3 or 4 functions and try it out and see what you get. Okay? All right. 3, 8, 3, 9, 3, 10 of functions. What do we know about a function? What do we know about a function? Give me some characteristics of something that is a function as opposed to a relation. Remember, a relation just relates coordinate pairs. That's all it does. It doesn't matter what they are. A function is a little bit more specific. I'll show you graphically, for example, if you recall. This is an example of a function. This is not a function. Why? Why? Danielle? Yeah, so here, for example, if I draw a vertical line, let's use blue, see how that works. All right. So I draw a vertical line there. I see that it's intersected here and here. So this coordinate might be like 3, -2. And this one would be then 3, -7. Who knows, right? Doesn't really matter. But the idea is that for every input, you should only have one output. For every x coordinate, you should only have one y coordinate. But look here. For the x coordinate of 3, don't you have 2 options? -2 and -7. Thus, it is not a function. Okay, again, what we were using here is called the vertical line test. That's what Danielle was describing here. But knowing how to use it with data as well. So if I give you... Sorry. I'm sick for like a week now. I'm finally trying to get over it. So if I showed you the first example at the top, you looked at it, you drew a vertical line anywhere Up here, right? Draw a vertical line anywhere up there. It's not going to cross more than one time with the actual graph. Okay, so algebraically, or I guess numerically, for example, if I gave you a data set like this, is it a function, yes or no? Is it a function, yes or no? And why, preferably? Yes. Why?
The x values don't repeat.
Yeah, very good. That's the easy way to remember. Good, Em. Look at the x values. There's no repeated x values, so there's no different y values for a given x value. But there are repeated y values. Don't let that throw you off, though, right? Very good. And a parabola always has repeated y values. Think about it. This coordinate here might be like -7, 2. This one is 2, 2. There's always going to be a repeated y value for parabolas. So you're going to see that happens a lot for the y values. But the x values cannot repeat unless for some crazy reason, and I don't know why I would do this. I wouldn't, honestly, but if for some reason like somebody was trying to trick you, this is still a function because I repeated 3, but it has the same output both times, right? So this is literally just rewriting that coordinate. It wouldn't make sense to do that. You wouldn't write the coordinate twice. So look for a repeated x value. That indicates that it is not a function if there's a repeated x value with a different y value. We looked at function notation in this section. So let's take a look at that. G of x. So we looked at linear functions for function notation. Okay, that was our actual general representation. It's the same thing as slope-intercept. Y equals mx plus b. But f of x is now a function of x. That's what y is. The value of, how do you get y when you're trying to find the coordinate? Say you know x is 2, how do you find y? You know x is 2, say you have an equation, right? X is 2, how do you find y? For that coordinate.
Just plug X in.
Yeah, you plug x in, and doesn't y depend on what you plug in? Y is your dependent variable. Y is a function of x, hence f of x. That's where this name and this whole idea comes from. It is called f of x because it is a function of x. Now, for this section, what we did were several things. We looked at evaluating functions. We looked at domain and range of functions. So let's do some examples of that. You should know how to do this both algebraically and graphically. And a lot of you struggle with the graphical portion on the quiz that we took. So let's start with that so we know how to do that. So let's say I've got the following. Let's say this is... It's not drawn to scale, just bear with me. Okay, and I said to you, what is the value of f of 4? Okay, what is the value of f of 4? How do you find the value of f of 4 graphically? What does it mean? What are you literally doing? F?
Finding the y coordinate that's next to 4.
Yeah, when x is 4, this is literally saying, if you need to write this down, write it down. This is saying when x is 4, find the function's value, which is the y coordinate. The y coordinate happens to be 0. So f of 4 happens to be 0. F of 8, everybody, f of 8? F of 2? What is it? -5. Remember, when you're looking for the function's value, it means you're looking for the y coordinate given the x coordinate. What if I said this? What if I said this, right? If I told you that f of x is equal to -5, what is x? If I tell you the function is equal to -5, what is x? Yeah, it's 2. Because clearly, 2 is what gives you the -5 here. So if f of x is equal to -5 and you want to find x, you can simply look at the x coordinate and say it's 2. Okay, but the idea of f of x and y is that functions being evaluated for a given x value, and you determine the y value as a result. What if I did this now? What if I did this? Oops. I can't erase, of course. I hate this program when it does that. I don't know why. Make believe this isn't here. I'm crossing it off, okay? And this isn't here as well. So now we have just a little segment instead of a line. We have a segment. with maybe a piecewise function, you might call it. Jeff, how would you figure out the domain and range for this? Do you remember what domain and range refer to? Like, what is the domain in general?
The domain is 2 negative 5 and 8 3.
Okay, but tell me in your own words, though, not with the answer from this. What is domain? Because domain and range are different. You kind of put them both together just now. You put domain and range together. But what is domain? You remember which one?
Domain is the limitation of what the values are later.
For which one? For x or y?
X.
Yeah, for x. So you don't need the -5 and the 3, right? Because those are the y coordinates there. You see that? So the domain in this problem would go from 2, right? Take a look. Where does it start on the x-axis? It starts at 2, and every x value up until 8 has some value. But after 8, do we know what these values are? No. So if I asked you to tell me what is f of 10, you would say it does not exist. Remember we did this on the quiz? If there's an open circle, let's say there's an open circle at 8. Okay, put an open circle at 8 up here instead of a closed circle. Then I could say also that f of 8 does not exist. Because remember, if there's an open circle, that point is not really on the graph. Open circles indicate you don't actually get to that. So the value of f of 8 does not exist if it's an open circle. Well, if I had this as my setup, my domain, I'll put the domain on the top left here, would be from 2 all the way to 8. Why did I do a bracket on one end and a parentheses on the other? Why did I do a bracket around the 2 for the domain and a parentheses at the 8, Sarah?
This 2 is included in 8, isn't it?
Yeah, 2 is a closed circle. It's included in the domain. 8 is an open circle. It's not included in the domain. Is that clear for domain? Yeah? So Jeff, follow it up now. You tell me for the range then. If that's what domain is, what's the range for this one? And again, open circle up at the 8, 3, closed circle down here at 2, -5.
Bracket -5, comma 3 parentheses.
Very good, Jeff. Okay, so see what Jeff did? Take a look. He started at -5. He said, well, the y value starts here, and the y values continue to occur, right? This occurs, this occurs. I'm literally like, imagine you're shining a flashlight from over here. You shine a flashlight. The shadow would start here. Imagine the rays are parallel coming out. The light rays are parallel coming this way, right? Here's the light rays. The shadow would end up going from here to here. That's your range. Okay, so it goes from 3, not including 3, all the way down to -5. Okay, including -5. Does that make sense so far? I'm going to trick you up a little bit now. Okay, so bear with me. Now, same graph, but add another function to it. Let's put a function, let me give me a sec to figure this out, to make sure this works. Okay, let's do this. Put something like that goes through the y-axis at some value above. Let's call this coordinate -2, 2. Call this coordinate 0, 3. And this endpoint over here, we'll call this, let's say it came all the way over, let's say it's 3.5, -3. It's hard to see those coordinates, sorry, but they're in yellow, okay? Look for the yellow coordinates there. So let's call this function g of x, somewhere on our graph, I don't know where, I'm putting it at the top for now. And let's go through this function evaluation process one more time. Let's go through the function evaluation process. So let me just slide this up so we have a little bit of room. So if I asked you to figure out what g of -2 is, what's g of -2? What is g of -2? So again, what am I asking? I'm asking the following. When x is -2, what's the y value for g's function? That's really what I'm asking, right? When x is -2, what is the y value for the function g of x? Will? Yeah, it's just 2. And where does Will get that? He gets it right here. Okay, on this endpoint. When x is -2, y is 2 for the g function. That's this right here. That's what that statement says. Now, how about this one? This is the one that threw a few people for a loop. What about g of f of 4? How do you do this again? And this is not algebraic. Algebraically, you plug it in the middle function, plug it in the outer function. Well, it's the same approach still. So do f of 4. What do you get, Sarah?
3.
But set me through at a time. F of 4 first is?
0.
So we start by finding this little piece right here, f of 4. And f of 4, here's f's function. Here's x equals 4. The y value when x is 4, the y value is 0. And we got that earlier. F of 4 was 0. So we realize that this is really like putting a 0 in its place because f of 4 is 0. Substitution principle. That's why you learn that. I know it's ridiculous to think about it, but that's what you're doing. You're substituting a 0 in for f of 4 because those are equivalent expressions. F of 4 is indeed 0. So because I'm putting a 0 in, now I'm really technically doing g of 0. And as Sarah mentioned, g of 0 is indeed 3. Okay, g of 0 is right here. When when x is 0, what is the value of the g function? Well, the g function is 3 when x is 0. Why is x 0? Because f of 4 itself is 0. Questions on this? So graphically, being able to look at the domain and range and also evaluate a function graphically. Now let's do that same thing. And algebraically, we only really look at the domain limitations. We don't really look at the range here, and you kind of know why. We talk about denominator and radicals and stuff. That has to do with x. Okay, the range limitations are easier to do graphically or more realistic. When we get to parabolas, you'll have to look at range, and that will be a limited range, but we haven't done that yet, so I'm not going to go into that algebraically. So algebraically, domain, and evaluate the function. So let's say the function is the following. What's the domain? It should be like about 3 seconds for you to do this. What's the domain? Come on, 3 seconds are gone already. If you don't know it, if you don't have it down pat, you need to study a little bit more. Domain? Sarah? It's not greater than -1. The denominator can't be 0, so x cannot be what? What would make the denominator 0? Yeah, so it cannot equal -1. You're doing it for a radical, that's why. We'll get to that in a minute. When it's just the denominator, remember the denominator cannot equal 0. So you start and you do this. You say this in your mind or you write it down. And then you say, okay, as a result, x can't equal -1. So my domain for this is x cannot equal -1. Or I could write my domain like this. Everybody see? First one is set notation. Second one is interval notation. It means the same thing. It means the exact same thing. Now, going back and looking further at this problem, if we had done this instead, ready? Put a radical around your denominator now. Well, a radical means that you have an expression of it that you're taking the square root of. You can't take the square root of what kind of number? What kind of a number can you not take the square root of?
Negative.
A negative number. So x cannot, or x plus 1 rather, cannot be negative. So if I were to do this problem again, I would start by saying this. X plus 1, it can't be negative, which means greater than or equal to 0, right? But it's in the denominator, so can it be equal to 0? No, it can't. So you just make that greater than 0 instead. Again, let me step you through this one more time. With a radical, you make the statement that the radicand must be positive or 0. But because it's in the denominator, it can't be 0. So it cannot use greater than or equal to. I need to erase that little equal to symbol underneath up here. And now it's just a greater than. I know you can barely see that with the blue, sorry. That's better. Okay, so it's just a greater than symbol. It's not a greater than or equal to symbol. You would do this if the radical were in a numerator, but it's in a denominator, and in a denominator you can't have anything equal to 0. So that would be your statement, and as a result, x greater than -1 would be your domain for this new function that we just recreated. what is f of 3 for this function? What is f of 3? Out? 3, careful. 3 over square root of 4, right? Assume the radical's there. The radical's there, sorry. 3 over 2, very good. Okay, so it's to be 3 over the square root of 3 plus 1. Remember, this 3 is taking on the value of x. It goes in for x up here, right? See that? So this has to be a 3. That's this 3. And as a result, we get 3 over radical 4, or 3 over 2. Function evaluation algebraically is actually quite simple, isn't it? You're literally plugging in a number and running it through that function. Now, if you also had a g of x function in addition to f of x, okay, and you wanted to do, let's say, g of f of 8. G of f of 8. What's f of 8? Do it in your head. You can definitely do this in your head. What's f of 8?
1.
1. If you plug in 8 here, you're going to get 8 plus 1, which is 9. Square root of 9 is 3. 3 over 3 is 1. So f of 8 is just 1. So what's g of 1 then? Chandler?
4.
4. Okay, again, take this 8, plug it in up here first into f of x. You'll get 3 over radical 9, which is 3 over 3, which is really a 1. Replace this with a 1. Do g of 1. So take that 1 and plug it in here. 3 times 1 is 3, plus 1 is equal to 4 as our answer. Okay, so work your way inside, out. Okay, always do what's inside the parentheses. You know that from PEMDAS, right? Always do inside the parentheses first. Then work your way outward. Questions on this? In 4.1 and 4.2, we started by going over a lot of terminology. You should know your terms. You should definitely know what those words mean. You should also be able to do word problems with these functions. Remember the problem we did where the tank is leaking gas at a certain rate, and you were trying to figure out when will the tank be empty, how much gas did the tank start with, those kinds of word problems. So 3.8, 3.9, 3.10, write down word problems, please. Write that down. We're not going to have enough time to go through an example right now. 3.8, 3.9, and 3.10 is where your word problems are going to come from for this test. I'm telling you now. Okay? It might be in 3.10 all of them. I forget honestly where it was that there were word problems. But look in those 3 sections in your book for function word problems. That's where your word problems will definitely be. What else? So 4.1 and 4.2 was properties of exponents. You have to know your major properties, some of them. The first one you can remember is like something like, whoops, can you see that? Yeah. X to the third times x to the fourth is x to the seventh. Okay, so your rule is when the bases are the same, add the exponents if they're multipliers. Another rule that we did, I'm trying to go back to all of our rules that we went through, jeez. We didn't do division with that. We did this, a power to a power. When you raise a power to a power, it's like writing x to the third 4 times, which would make it x to the 12th. So you multiply those powers. What else? What were the other rules? We did like 2 or 3 rules. Anything to the 0 is? Good. Always. Anything to the 0 is always 1. I feel like there was one more rule that we had also. Oh. I think we did one where we had multiple things inside and we had a power on the outside, such as this. This becomes what? What does this become?
X is 6 plus.
Yeah. This should be quick, guys. This should be like, I'm not trying to be mean, but you should be able to answer a question like that in like 2 seconds. 3 times 2 is 6, 5 times 2 is 10. Okay, I need to see more hands. Others need to volunteer. It seems like you don't know it or you're just sitting there. You should be able to multiply polynomial functions. That's polynomial functions. We did all of that in the last section. So when multiplying things, remember to double or triple distribute depending on what's going on. So something like this, we've got a trinomial times a binomial. You could use your table method, like that. X squared, x 5, 2x, and negative 7 there, and literally go through, or distribute once, distribute twice, distribute 3 times. Collect all like terms. Okay, collect all like terms afterward. We have time, let's do a work. Let's see what we're at. 22, yeah, less than. Okay. Questions? Yeah.
Are the problem sets going to be up today?
Are the answers going to be up? Did anybody not turn their problem sets? That's really the question I have to ask. You have to turn yours in still? Problem sets are due. It's always good to do before the test.
Yeah, it's slipped my mind.
Okay, but the test is tomorrow, right? So the answer will be no. But if you have a question on something, email me. Guys, if everybody turn them in, I don't put the solution up. But if you have a question on a problem, specifically, and you're looking at your homework and you're studying tonight, and you're not sure how you got it, if you got it right or not, I'll send you the solution to that problem individually. I can do that, it's fine. Okay, so just let me know if you're done with yours and you have a question, I'm happy to reply with an answer to it. I'll just send you the solution to that problem, specifically. Other questions? I don't know how many points it's going to be. It's probably going to be like 60 points. But remember, this quarter it's only 2 tests. We're doing test 4 and 5 kind of together here, and then test 5 and 6 at the end of the quarter together. Your project for the second quarter is already up, but don't focus on it tonight. Okay, tomorrow we have the test. Next week on Tuesday when I have you, it's a C day. So I thought we'd spend that day at least just going over what the project's going to be. You're welcome to look at it over the weekend, but it's not necessarily something you can easily start. You might want to wait, okay? All right. Have a good night. Enjoy your studying. Get your problem sets into me if you haven't done so already. Hey, if you guys finish your problem sets tonight, at least take a picture and send me a scan of it so I know it's done. For those that didn't get a chance to yet.